Check out this paper bridge. Poor fella, he's having trouble just holding himself up, and when we try to add a load to him, he immediately gives up. Now, check out this bridge. He's an identical piece of paper, but folds it into a zigzag shape and has no problem holding himself up. He can even hold up some decent weight before remembering that he's just a piece of paper and giving up. He's not the best bridge, but he handled weight significantly better than his unfolded friend. He even handled the faults in our stars without breaking down, which is something I can't say about myself. How cool is it that a very simple geometric change can make such a vast difference in the behavior of a material? In this video, we're going to try and understand how we can quantify the bendiness of something based on its geometry, whether it be a sheet of paper, a floppy slice of pizza, or a structural beam. Let's start by considering this beam. Its bendiness is a bit exaggerated for the sake of visual clarity. We should notice that when we bend the beam like this, the surface at the top has to get squished, while the surface at the bottom has to get stretched out. If we cut the beam up into horizontal layers, we can see a pattern where the layers get shorter as we go up and longer as we go down. I'll try and explain it later, but for now, let's assume that there's a layer in the middle that stays the exact same length. We'll call it the neutral layer. In the case where the layer is infinitesimally thin, it is called the neutral plane. If we draw a circle tangent to this layer, we can use its radius to quantify how much the beam bends. It's convenient to define the quantity kappa for curvature as the inverse of the radius. If curvature is 0, the beam is completely straight. If the curvature is negative, the beam is bending the other way. If the length of the beam is L, and the angle subtended by the layer is theta, then we get the relationship L equals theta times R, or L equals theta divided by kappa. Let's find the length of a layer that is y units above the neutral layer. Its tangent circle is concentric to the neutral circle, so we can easily find its radius as r minus y, or 1 over kappa minus y. We can write its length in terms of theta, like so. Let's introduce another really convenient quantity, strain. Strain is basically the ratio of the length gained or removed by stretching or squishing a material relative to its original length, so it is used to measure how strong the stretching or squishing really is. Since the unbent length of the squished layer is the same length as the neutral layer, we can find the strain by dividing these two lengths, which simplifies very nicely to negative kappa times y. We need yet another convenient quantity, stress. It's basically a way to measure how force is distributed across a cross-section. We will make another really convenient assumption that stress is proportional to strain. This approximation is decently accurate for most materials when the stress isn't too big. The constant of proportionality between stress and strain is called Young's modulus of elasticity, or capital E. Hence, the stress of the layer is negative E times kappa times y. From here, we can visualize the distribution of stress in the beam. As we travel above the neutral axis, the forces squish inwards more and more. As we travel below the neutral axis, the forces stretch outwards more and more. Now, we can gain a better argument as to why and where the neutral plane exists. If there are no external forces acting to stretch or squish the beam axially, the forces we see in this distribution must cancel each other out, and that just so happens when the line where the internal force is 0 passes through the centroid of the cross-section. Although the forces in this distribution must cancel out, there is still another valuable quantity that we can get, the bending moment around the neutral axis. Essentially, how much are the forces trying to twist around the neutral axis? Since axial stress equals force over cross-sectional area, we can calculate the force on a layer by multiplying the stress by the height and width of the layer. A moment is calculated as force times distance away from the pivot point, so we multiply the force quantity by y. Finally, we sum up all the moments of all the layers to get the total moment over the cross-section. To take the limit as the layers get infinitely thin, we turn the sum into an integral. We can pull out the constants e and kappa outside the integral sign. The remaining integral is called the second moment of area, or capital I. It depends purely on the geometry of the cross-section. The more the cross-section area is accumulated away from the neutral axis, the bigger I gets. Now, let's rearrange this equation. We get that kappa is equal to m over ei. Can we appreciate how pretty this equation is? The curvature of a beam is isolated into 3 simple distinct factors. M encompasses the result of external loads on the beam, E encompasses the rigidity of the beam's material, and I encompasses the rigidity of the beam's cross-sectional shape. We see that I is inversely proportional to curvature, which makes a lot of sense. The bigger I gets, the further the material of a beam is spread away from the neutral axis, and the more stress that far material will have to experience to allow the beam to bend. That's why a lot of beams in real life have an I-shaped or U-shaped cross-section. Most of the material is accumulated in the flanges far away from the neutral axis, making these beams way harder to bend. Now, let's apply this to the example of the paper bridges from earlier. When we take a look at the cross-section of the flat piece of paper, we can tell quite easily that its second moment of area is very small because all the material is clustered close to the neutral plane. This makes it bend easily and fall between the chairs. However, when we add the zigzag folds to paper, more of the material is moved further away from the neutral axis, so the second moment of area gets way bigger. The paper is therefore able to resist bending, so it doesn't fall between the chairs. The same principle is used in corrugated cardboard and corrugated iron to increase their rigidity. Let's also apply these curvature principles to a pizza slice. When you just hold the crust flat, the cross-section has all the material clustered around the neutral plane, so the pizza will very easily flop. Now, if we fold the pizza and analyze the cross-section, this U-shape brings a lot of material far above and below the neutral plane, preventing the slice from flopping, making it easier to eat. One more somewhat relevant example, and this is maybe the coolest one. You may be familiar with the concept of thermal expansion. When you heat up a piece of steel, it will expand. When you heat up a piece of brass, it will expand, but much more. Now, if you bind a strip of steel to a strip of brass and heat that up, just like when analyzing the beam, we have a skewed distribution of strains, and hence stresses, so the strip will ultimately bend and curl. This is called a bimetallic strip, and it's a really clever way to move things based on temperature without the need for any external power or motors. These devices are used in thermostats, activating a switch by bending when heated or cooled. They're used in circuit breakers to break the circuit when the current is too high. The strip bends when it gets heated up by an excessively large current. They're even used in satellites to passively control the angles of these blades called louvers, which can increase the amount of heat radiated out into space. Thank you so much for watching this video. I hope you enjoyed it, and I would love to hear your perspectives in the comments.